The section on infinite limits is going to use everything that you've learned about finding limits so far to strengthen your understanding about functions that increase or decrease without bound. We will be looking at limits from both the one-sided and two-sided perspective. In addition, we're going to fine-tune your skills on sketching graphs of functions that have issues with their domains. It's important for you to remember that your graphing calculators have difficulty graphing asymptotes. Therefore, you need to be very sharp at identifying where the domain issues are in your functions. Let's look at rational functions first. Rational functions get into trouble when their denominators equal 0. When this happens, vertical asymptotes might show up. So set your denominator equal to 0, find the x values at which this occurs, and then determine are these removable or non-removable discontinuities. Remember, the non-removable discontinuities are the vertical asymptotes. Now looking at horizontal asymptotes, we look at our functions and we want to look at that leading term in both the numerator and the denominator. Comparing the exponents of the leading term, we look and see if n is less than m, then the horizontal asymptote is the x-axis, or the line y equals 0. If n is equal to m, we want to take the ratio of the leading coefficients. If our n is greater than m, we won't have a horizontal asymptote, but a slant asymptote might show up. If n is exactly equal to m plus 1, you do long division to find that slant asymptote. Now, other functions that have trouble are trigonometric functions. Remember, sine and cosine are continuous everywhere, but the ones that use them as their denominators are not. So anytime that sine is equal to 0, cotangent and cosecant are going to have an asymptote. And likewise, when cosine is equal to 0, tangent and secant are going to have an asymptote. So use sine and cosine as your guides to sketch the other functions. One technicality that I want to make sure that you're very good at determining the difference between is the phrase limits of infinity versus limits at infinity. So I've sketched a generic little function to help us in our discussion. If I look at a function and I say, as my x value approaches this value of a, I want to know what the function is doing. And as we can see, both sides, my left and my right, are approaching positive infinity. Then I say my answer is infinity. This type of a situation is a limit of infinity. When I have a limit of infinity, it means infinity is my answer. However, if I look at a limit at infinity, at this point, I'm asking you to look at what's happening to the function as your x value goes off towards infinity. So as my x value goes off towards infinity, notice my horizontal asymptote is having a huge effect on my graph and pulling that graph towards it. And so it's very important that you understand that your horizontal asymptotes are going to come into play when we look at limits at infinity. This will occur in sections 3.5 and 3.6. But for now, keep your focus on limits of infinity, where infinity is a choice of an answer. Starting with our first example, we're looking at the limit as x goes to 0 of 1 over x. I know this function goes undefined when x equals 0 and that it's a non-removable discontinuity because I can't make it cancel. Therefore, I have a vertical asymptote at the point where x equals 0. So that is going to be my vertical line that is imaginary. That's my vertical asymptote. Likewise, I look at my numerator and denominator. My exponent of my leading coefficient in the numerator is 0. My exponent of my leading coefficient in the denominator is 1. Therefore, n is less than m. And my horizontal asymptote is the x-axis, or in other words, that horizontal line, y equals 0. So I took a quick break and drew our graph so that we could take a look at it. And as I look towards 0 coming from the left, I can see that my function follows the horizontal asymptote, but then is grabbed by that vertical asymptote and shoots off to negative infinity. And on the right, as I come in from positive infinity approaching 0, my graph follows the horizontal asymptote, but then again is grabbed by that vertical asymptote and shoots towards positive infinity. Because my two limits do not equal each other, I have two problems. First, my limit does not approach an exact value. So even if I could say, oh, they both approach the same value of infinity, I can give you a description of what's happening, but again, it doesn't mean that the limit actually exists. The other problem that I have is the fact that the two limits, the limit from the left and the limit from the right, are not approaching the same value. I've got negative infinity and positive infinity, which are not equal. Therefore, I say definitely my limit as x approaches 0 of 1 over x does not exist, because the function is diverging as x approaches 0. Now in this example, as we look at the function 1 over x minus 1 squared, and we want to take the limit as x approaches 1, we can see that we have a non-removable discontinuity where x equals 1. So we have a vertical asymptote at x equals 1. In addition, we have the same relationship we had before where n is less than m, because our exponent in the numerator is 0 and our exponent in the denominator is 1. So again, our x-axis, or the line y equals 0, is our horizontal asymptote. Now looking at the graph, we want to look what's happening as x approaches 1 from the left. Well, putting any negative values inside and then squaring them in our function is going to keep us getting positive values of our y. So as x approaches 1 from the left, our function is above the horizontal asymptote, and then as it gets closer to 1, it's going to shoot off towards positive infinity. So the limit as x approaches 1 from the left is infinity. Now, coming from the right, again, it's above the horizontal asymptote, and as it approaches 1, that vertical asymptote takes over and shoots it off to positive infinity. So the limit as x approaches 1 from the right is also positive infinity. Now, we still have the problem that they're not approaching an exact value, but what I'm doing is describing the behavior of my graph using the limit process. So I say that my limit as x approaches 1 of 1 over x minus 1 squared is equal to infinity because the function is converging as x approaches 1. However, this is not to be confused with the idea of saying that the limit exists, because it doesn't. It's not approaching an exact value. Now let's take a look at the limit as x approaches 2 of x cubed minus 8 over x minus 2. Now before I say that there's a vertical asymptote at 2, I want to take a look at the function and see if I can simplify it. So using my difference of cubes, I factor the function. When I do this, I notice that now I have a common factor that I can cross out. So what does that mean? It means that it's a removable discontinuity and I have a hole at x equals 2. So now, taking a deeper look at my function, I want to put it in a graphical form of a quadratic so that I can graph it very easy. I know that its vertex is at -1, 3 and that it has a y-intercept of 0, 4. As we take a look at the graph, now we're looking at a parabola that doesn't have an asymptote. It simply has a hole when x was 2. So if that value existed, my y value would be 12. Notice that my limit as I come towards 2 from the left and my limit as I come towards 2 from the right are both approaching that y value of 12. Therefore, the limit as x approaches 2 of x cubed minus 8 over x minus 2 is equal to 12, using both a graphical, numerical, and an analytical method. Now it's time to look at a trigonometric example. I want to take the limit as x approaches 3 from the right of the secant of pi x over 6. So knowing that secant is the reciprocal of cosine, it's going to go undefined when cosine is 0. So I'm going to use cosine as my guide. So I start making my list so that I can graph cosine as a ghost graph. I have an amplitude of 1. The period using 2 pi over b is equal to 12. I set my cosine equal to 0 so that I can identify where the secant is going to have asymptotes. And I discover that they're going to occur at x equals 3 and x equals 9. So let's graph it. So using my graph of cosine as a ghost, I know that secant is going to share the max and min values at 1 and -1. So I join at those points, and then I follow the asymptote to tell me where's the graph going at those points. So now that I have it sketched, I want to take a look as x is approaching 3 only from the right. So I'm right here following this asymptote that's just at 3. And you notice that my function is going to -infinity. So my answer, because it's a one-sided limit, not a two-sided limit, is the limit as x approaches 3 from the right of secant pi x over 6 is -infinity. Now, it's your turn. I have three small problems for you. Your answers are going to either be numeric or a short symbolic answer. And then, because we're at the end of the chapter, I'd like you to write a brief summary. Be very descriptive. How do we find limits? What type of answers can we expect to find? And you might want to explain why. And what do limits tell us about functions? Finally, don't forget to write down your homework, and I'll see you in class tomorrow.